IP addresses are like the home addresses of devices on a network. Every device connected to the internet, your phone, laptop, or a server, needs a unique IP address, so data knows exactly where to go. In most modern networks, devices don't manually get these IPs. Instead, they receive them automatically from a DHCP server. When your device connects to a network, it sends a request for an IP address, and the DHCP server assigns it an available one along with other settings like subnet mask, default gateway, and DNS. This process happens through the DORA process: discover, offer, request, and acknowledge, where the device first discovers available DHCP servers, receives an IP offer, requests to use it, and finally gets it acknowledged and assigned. In home networks, this DHCP function is usually handled by your router, while in enterprise environments, it can be hosted on a Windows server running DHCP services or configured on a core Layer 3 switch, which centrally manages IP distribution across large networks. Now, IP addresses come in two main types: private and public. A public IP address is globally unique and can be reached over the internet. It is what websites, servers, and online services use so that users around the world can access them. On the other hand, private IP addresses are used within local networks, such as those found in homes, schools, and businesses. These private IP ranges are not directly reachable from the internet, and their address ranges are shown in the table below. Because they are intended only for internal communication, the same private IP addresses can be reused across millions of different networks worldwide. Since private IPs cannot directly access the internet, they rely on a process called network address translation. NAT is usually performed by a router or firewall at the edge of the network. When a device with a private IP tries to access a website, NAT translates that private IP into the network's public IP address. This allows multiple devices inside a private network to share a single public IP while still accessing the internet. When the response comes back, NAT maps it back to the correct internal device. This is a key concept in cybersecurity because it hides internal network structures from the outside world and adds a layer of protection. When data travels across the internet, it is broken into small pieces called packets. Each packet contains the source IP address, destination IP address, and the actual data payload. These packets move through routers, which act like traffic controllers. Each router reads the destination IP and forwards the packet to its next hop. Packets from the same message don't always take the same route, which makes the internet flexible and resilient. Packets also have a limit called TTL, time to live, which is like a built-in safety counter that prevents them from circulating endlessly in the network if something goes wrong. Every time a packet moves from one router to another, the TTL value is reduced by 1. If the packet is caught in a routing loop, for example, due to a misconfigured network where routers keep forwarding it in circles, the TTL keeps decreasing until it reaches 0. Once it hits 0, the packet is automatically discarded, and an error message is usually sent back to the sender. This ensures the network stays stable and doesn't get overloaded by stuck or looping packets that would otherwise consume bandwidth forever. Finally, subnetting organizes large networks into smaller segments called subnets. Think of it like dividing a city into neighborhoods. Each subnet groups devices together for better performance, easier management, and improved security. In cybersecurity, subnetting is crucial because it restricts how far an attacker can move inside a network and helps contain potential breaches within smaller sections instead of spreading across the entire system. Thanks for tuning in. Please like and subscribe.